Okay, real quick, again, we're going to have a little discussion about airflow characteristics over different surfaces. So, this one in regards to like a cylinder head port. So, I got asked once, and I was in the presence of another engine builder and someone who really didn't understand engines very well. They're a road racer driver. But they asked me a question. I gave them the dumbed down answer, and I got looked at like I was an asshole by the other engine builder. But I was correct, and also so was he. So, sometimes it's the same way of saying the same thing, just differently. What I said is, well, when you put dimples or really hard edges in a port trough, like the trough style, like when you see like a CNC tool path that goes horizontally, like if you're looking down the port and it goes like this around the port as it travels down the length of that port, if they're coarse enough, does the same thing effectively to that port that dimpling does in a port. Just different ways to get to the same point, if you will. And I'll demonstrate what's going on here. So my red marker is my smoothly sanded port. So air is going to come in. Air always wants to take as straight a path as possible, but as room is made, especially in the bowl area of your port, it will turn the short side, but a majority of this air is going to want to come that way, right? So we'll put 2 arrows in that one and 1 arrow on that one. So that makes sense? Okay, so this is normal airflow in this port. It can hug very tight to the wall here because there's no texture here. It doesn't, up here there's still a dead area of the port because there's just so much volume. Part of which that slowing down of the air as it comes down is what allows it to turn the short side, because if the port's really small, it doesn't even want to do that. You get more and more air to the far side of the valve here, or as you would call it, the long side radius of the port. So that's your basic smooth, very smooth finish wall port. Now, why does that differ if you have a coarse CNC machining pass or if you dimple it? Well, let me get my red marker and I'll redraw this a little bit for posterity's sake. So, if we have a CNC or a dimple on our port, and this basically boils down to what me and the other engine builder were having the agreeable disagreement on, which was saying the same thing in different ways, right? This is a fun one. So now we've redrawn this is like a cross-sectional view through your dimples or your rough CNC pass. It's a little exaggerated, but it gets the point across. What's going to happen here is the air itself, and he's right and I'm right in this regard, is going to move over these peaks and valleys and do the same thing. And the air up here is also doing the same thing, moving through peaks and valleys. It's following that wall roughness, right? So as opposed to the air that's in the center of the port here, which is still moving in basically a straight line, the air at the edge is moving in a longer line. It's physically following the texture all the way through. And what does that do? Well, this air moving this manner causes this air, instead of being as tight to the wall, the airflow path moves up more away from the wall, like so. So by rights, that airflow path is now constricting itself. More of the air is moving more rapidly at the center of your port. And why is that important? Well, in the cylinder flowing world, or the cylinder head flow world, you're trying to move air to a more desirable point. So by placing this thing that creates, for lack of a better term, an air, not a void, it creates more room, but at the same time creates an air pocket that's slower moving air. Well, it's moving the same speed, it just has to go further, right? So, but basically relative to that air that's at the edges where that texture is, takes longer to get from A to B than the air in the center of the port. So you build a constriction point with air. In other words, you're building a pocket of air that is moving the shape of the port relatively to. And that can increase airflow velocity, which velocity is another way to build port energy without RPM, which also builds power. But it is a double-edged sword. So depending on the application, the size of the port, how lazy the port is, where the port is lazy, and again, you have to take a lot of airspeed measurements to figure this out. Where is the sweet spot on combination of textured ports versus smooth wall ports, and size of the motor, valve train layout, 4-valve, Hemi, or a a wedge style head or a canted wedge head, same thing, for all intents and purposes. So this is how that applies. And it's just a funny argument to have had with another, not even an argument. We weren't really arguing. He just looked at me like I was a dick. But maybe because in a way, what I was really doing was just oversimplifying what I was talking about for someone who wasn't as familiar with the concepts. And it's a funny, like I said, it's a funny way to say the same thing differently, but it has the same effect. And the end result is the effect that I said. It's where you basically are slowing down the air relative to. In other words, if you measure two molecules, point A, one on the edge of this rough port or rough area that starts into it and starts bouncing and moving through versus the ones towards center, the center is moving faster. In other words, and you can actually constrict the shape of a port, or you can reshape a port using air eddy currents, essentially, that are created by this to do so. It's the same principle as what's happening on a golf ball, just inside an orifice. All right, that's all I got. Have a good one.